Right, you should have out your lecture notes for lecture 17, a little bit more on probability. All right, so we've just got a few more concepts that we should get out of the way before we can start talking about random variable theory. It's random variable theory that will allow us to get to inferential statistics. All right, so our context, I'm not going to write it up here, is, well, I guess I will say we have a random experiment, just kind of summarize it. Random experiment, sample space, which means the set of all possible outcomes, and we usually call that S, and we have some event, E, and that is, we think of that as some subset of S, some set of the outcomes from S. All right, and I want you to recall the classical probability. This is what we think of as really essentially the true probability, if you want to say, of the event E. That's equal to the number of things in the subset over the number of things in the sample space. And that's the case where we have a sample space that has just a finite number of outcomes in it. It's a number in E over a number in S. And really, more generally, it's the measure of E, however we're measuring it, and we saw an example where we had to measure it with area, right? We had to measure the sample space and the particular event with area. So in general, it's really this size of E over size of S, but a lot of the examples will work, a lot of really practical examples. It just boils down to count the number of things in E over the number of things in S. And again, we're assuming equally likely outcomes, right? Here. Okay, or that goes up there because if we don't have equally likely outcomes, then we saw we can't just count the number of things in E and divide by the number of things in S. We don't get the right answer that way. Empirical probability. And we define that as probability of E, and we think of this as generally an estimate of the true probability up here, but I'm using P of E, the same symbol as I use up there. It is the number of times E occurs over the number of times E occurs over the number of times we perform the experiment. All right, so why is it called empirical? It's because you're actually going out and doing the work of performing the experiment over and over and over, and each time you're counting when E occurs, and then after you've done it many times, you count the number of times E has occurred and divide by the number of times that you've performed the experiment. Up here with the classical probability, we're not doing any of the experiment at all, correct? We are just figuring out what the set of possible outcomes are, assuming they're equally likely, and the number of outcomes there are in E, and under the assumption of there being equally likely, we just do the division. There's no actually performing the experiment. Yeah, and I guess I say down here that the empirical probability is thought of as an estimate of the classical probability. I think I can get it in right here. I think I have room. The empirical probability, the way I would indicate this is that I would say it zooms in on or approaches, we might say converges to the classical probability, and that is as the number of experiments, the number of times the experiment is performed, grows without bounds. And how do we indicate that? Well, we can indicate like this, arrow to infinity. So this arrow here is telling me that the empirical probability is zooming in on the classical probability, and this stuff up here above the arrow is the condition under which that happens, and that happens if the experiment, number of times I perform the experiment, grows and grows and grows forever, essentially, right? And this is what we really mean by the law of large numbers. All right, that's where we were last time, and I want to just ask you to think here a little bit about how we're calculating the probability, either looking at the classical case or the empirical case. In each case, we have a fraction. We have, for the classical probability, we have the number of things in E divided by the number of things in S. In the empirical case, we have the number of times E occurs divided by the total number of times we perform the experiment. And what do I say? I say that let's compare the numerator and the denominator. So note, in a probability, let's say fraction, well, in a probability, we have a fraction, and of course, since E is a subset of S, the number of things in E will never be bigger than the number of things in S. And likewise down here, the number of times E occurs can't be more than the number of times we actually perform the experiment and get any outcome. So in a probability, the numerator is never bigger than the denominator. All right, what does that mean? The numerator is never bigger than the denominator. So, probability of E is never bigger than 1. Right? It can't possibly be bigger than 1. And intuitively, if you think 1 means 100%, you can never be more than 100% sure something is going to happen, right? So that should make intuitive sense. In fact, we have the following fact. The probability of E, I just said it's less than or equal to 1, right? But we can add something more to that, and that is, look at how it's calculated over here. I'm counting, right? I either count I'm doing some kind of measurement. I measure the size of E divided by the size of S. This is going to be some positive number here in the numerator divided by some other positive number. The result is positive, or at least non-negative, let's say. The top could be 0, but it could never be negative, and neither could the denominator. And likewise down here, if I'm counting the number of times the event occurs and dividing by the number of times we perform the experiment, those numbers are never negative. So I'm always going to get a positive number. So the way we can illustrate that is by saying that the probability of E is between 0 and 1. In fact, that's the way you might want to say it. The probability of an event is always between 0 and 1. The mathematically concise way of writing it is right there. 0 is less than or equal to the probability of E is less than or equal to 1. This is true for all events, anything you can think of. So I say down here, let's just have some examples of numbers that could be probabilities. So possible probability numbers. Possible probability values. Can't spell probability. Possible probability values for some event could be, well, 1/2, right? That's the probability of getting ahead if I toss a fair coin. So there are two possible probabilities, or two possible outcomes, and I'm interested in 1. So it's 1/2, of course. Maybe 1/6. That could represent the probability of getting a 3 if I toss a fair die, as we've done before, et cetera, et cetera. 7/10, 0.0293, right? That could be 1. How about 1? The answer is yes. That could be a possible probability value. We'll look at that in a second here. And let me go ahead and stick the other extreme on, is 0. I can't get bigger than 1. I can't get less than 0. Let's have some not possible probability values. -2. It can't be negative. +2. It can't be bigger than 1, right? Well, that's about takes care of it. I can't have 1.00003. All right, that's bigger than 1. I can't have negative 0.001. All right, that's a negative number. All right, I could have positive 0.001. That's 1 in 1,000. All right, but I can't have negative. Okay, I just put a few of those up there just to help you kind of solidify in your brain the probability has to be between between 0 and 1. All right, and then I think I'm doing a sure event. So definition. a sure event, what do you think? It has probability 1. So a sure event E has probability of E equal to 1. 100% probability. So, for example, toss a fair die. All right, and the sample space we know is, let me write it out. Sample space is 1, 2, 3, 4, 5, 6. All right, let's let E equal, get a number less than 8. All right, and ask yourself, if I toss a normal fair die, what's the probability I'm going to get a number less than 8? The answer is, well, it's a sure thing, 100% probability, right? And we can just kind of mindlessly calculate what that answer will be. E as a subset of S, of course, is, well, is the outcome 1 less than 8? Yes. Is 2 less than 8? Yes, etc., all the way up to all the possible outcomes. So what's the probability of E? It's the number of things in E divided by the number of things in S, and that's 6 over 6, so it's 1. That's a very roundabout way to get an answer that you already know is 1, but you can see it works with all the theory we've developed so far. What about an impossible event? I bet you can about guess. An impossible event, event F, is such that, I'm just going to say has, the probability of F is 0. All right, so impossible means 0% probability. So how about above? We have the same context as above, but the example would be let F equal die lands on 2.5. All right, is 2.5 an actual possible outcome? The answer is no. So as a subset of the sample space, it's just the empty set, correct? So what's the probability of F? It is the number of things in F divided by the number of things in S. And let's see, I have room to do this. Indeed, that's in the empty set, there's no things, and the set S, there's 6, and 0 divided by any non-zero number is 0. So the probability is 0%, in fact. All right, and got a little bit more to do here, and I do have to rub this out. Okay, so bear with me. We've got different markers, so it's a little easier to rub things out fairly quickly. We don't have the old stuff created kind of a mess. We don't have that so much anymore. You had a mess and you had to dry it off and all that, so it didn't work to rub things out in the middle of a lecture, but I can do it at least a little bit now. Let me switch colors so that we can tell, and I'm talking about something new. Okay, given an event E, what's the complement of E? Definition. Given an event E, so our context is we have some random experiment, some sample space, some subset of the sample space E. We say that E bar, the complement of E, is the subset of the sample space containing everything else outside of E. All right, so it's the subset that when you figure out what E is, the complement of E is everything else. All right, so the two don't have any what we call intersection. They don't overlap at all. And together, when we put them together, they give you the whole sample space. All right, so, for example here, we could say this. Example, so I have the same context that I have over here. Let's let E equal, we get a number greater than 2, okay? E is 3, 4, 5, 6. So E complement would be what is not in here that's in the sample space 1, 2, 3, 4, 5, 6. The answer, of course, is 1, 2. And we could say that that's get a number less than or equal to 2, isn't it? So the complement to getting a number greater than 2 is getting a number less than or equal to 2 here. All right. Yeah, let me just go ahead and say, notice then, so what we have is that since an event E and its complement are separate completely from each other, they don't overlap, and together they make up the whole sample space, we can go through just a little bit, you do an example, do a little arithmetic, but it should be pretty easy for you to see that if I have E and E complement, the probability of E and E complement, those two things together take care of the whole set, so this better add up to 100%, right? It better add up to 1. So what that really says, and this is what's important, so I can compute the probability of E complement by just doing a little arithmetic here. If I know the probability of E, let me subtract probability of E from both sides. This gives me 1 minus the probability of E. That's an important formula. If I know the probability of E, I can compute the probability of E complement real easily just by doing 1 minus. Or, and we can just turn it around, suppose I want to know the probability of some event E, that's just 1 minus the probability of E complement. And these formulas really are saying the same thing. Since E is the complement of the complement, once I have this formula, this one is just automatic, right? But they both come from doing the algebra, right? Doing the little subtraction right there. Okay, and I guess I have one example of that. Who cares about that? Well, it can actually be quite useful. And we will see it come up several times in the future, but let me just give you one example right now. Okay, so think of the example where a couple had 3 children. And we were keeping track of the genders. S was an 8-point set. Girl, girl, boy. Or sorry, girl, 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 boy. Girl, boy, girl. Girl, boy, boy. Boy, girl, girl, boy, girl, boy, 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 girl, boy, boy, boy. Okay. And let me say the event E is they have at least one boy. All right, and if you remember, we actually did this problem. We computed the probability that the couple would have at least one boy. And what we did is we figured out what that was as a subset of the sample space. And it turned out to be, all of these, and we got a probability of 7/8. All right, but let me just ask, what's the complement? The complement of having at least one boy would mean the exact, everything else would just mean having no boys, right? So this is have no boys. And so that's just the element of the sample space with one thing in it, right? It's just the subset that has just one element in it. And that probability is really easy to compute. It's really easy to count the one thing. So the probability of E complement, that's E complement, is 1/8. So what we want, the probability of E is 1 minus 1/8 using that formula right there. And it's 7/8. Okay? Now in this example, it's not that hard to just count up and get, okay, there are 7 in the event E, so the answer is 7/8. It's a little easier to just see, okay, in E complement there's 1 and do the 1 minus 1/8 perhaps, but we are going to see examples in the future where it will be much easier to compute the complementary event than to compute the event that's the probability of the event that's asked for. So it's useful to begin to understand this. And we'll stop there.